Welcome all. Let us see how two fixed point binary numbers can be multiplied. A computer can multiply two fixed point binary numbers in various ways. If the numbers are in signed magnitude form, that is, there is a bit for sign and there the remaining bits are for magnitude. If it is in this form, then we follow a particular method. In fact, we follow the if we do this signed magnitude multiplication on paper, it will be just like a normal multiplication as we do a multiplication of decimal numbers. So this is 23. This is the magnitude of 23 here. There will be an extra bit for sign. And this is 19. This is the magnitude of 19 here. And there will be an extra bit for sign. In this example, we are supposing that only this is a 5-bit thing only here. It can be of 7 bits or even more. When we multiply these two here on paper, we just do it like normal multiplication. So this is the multiplicand and this is the multiplier with which we have to multiply. So this whole thing is to be first multiplied by 1, this thing, then by this, then by this, then by this, and then by this. So this whole thing multiplied by 1 will come this. Then we on paper we move a place here. Then we multiply this whole thing with 1. Again it comes out to be this. Then with 0 it comes out to be 5 zeros. Then again with 0 it comes out to be 5 zeros. Then again this multiplicand is multiplied with 1. It comes out to be the same multiplicand here. And then after these 1, 2, 3, 4, 5 steps, 5 steps because there are 5 bits here. So then we add up these, we just add up these and we get an answer. So answer will be obviously large and very large than these two. And if you calculate this will be 437. This is just the magnitude. And if we consider the sign also here, then we again have to do the same thing, the exclusive OR. If both are positive, so its sign will be 0, its sign also be sign bit will be 0. Exclusive OR of both bits will be again 0, so the answer will be positive. So the exclusive OR of both the signs will be the sign of the answer. Again, if both are negative, then that means here the sign bit will be 1, here also the sign bit will be 1. So 1 and 1 exclusive OR comes out to be 0, so the answer will be positive. If this is negative and this is positive, exclusive OR will be 1, that means the answer is negative. If this is negative and this is positive, or this is positive or this is negative, again the exclusive OR will be 1, so the answer will be, logically speaking, it will be negative, it should be negative. Then what will be the hardware required for this multiplication? Interestingly, you don't need any multiplier thing here, you just need that old hardware, the same hardware which we can use, which we use in addition and subtraction. In addition and subtraction, we use an A register, we use a B register, and we use these flip-flops for storing the signs, an E for carry, and an adder and a complementer. So in multiplication also you need the same hardware, you don't need to create a new hardware. But in addition to this addition and subtraction hardware, you just need two more registers. One register for counting purposes and the other for some other purpose that I will tell you later. So this here is the uh, hardware that is used for multiplication. So here on the left hand side, on your left hand side, you can see this flow chart. This flow chart is a flow chart which if we follow, we will get an answer which will be a multiplication of the two numbers. This flow chart is specifically meant for those numbers which are in signed magnitude representation. So you need to remember this flow chart to do a multiplication thing. So how does this work? Let us see through an example here. So let us take two numbers. So one number is 10111, another is 10011. So 10111, 10011. So this is the multiplicand, this is the multiplier. So this is actually 23, the magnitude, and 19 is this. So we had to do a multiplication of 23 and 19 using this hardware, and this can be done only by following this flow chart. This will be the process for used by the computer to do this multiplication. So first thing, the multiplicand will be stored in B, this register, B register, and the multiplier with which I have to multiply will be stored in Q, means this register. I am repeating, the multiplicand will be here, the multiplier with which we have to multiply is to be stored here. The sign bit of the multiplicand will be here, the sign bit of the multiplier will be here. This sequence counter will store how many bits are there in this multiplicand, in this multiplier. So the number of bits in the multiplier represents the sequence counter. This many times I have to do the multiplication. And here this Qn is the name of the rightmost bit of this register. Fine, let us start with this thing now. So I have to do a multiply. First I put multiplicand in B, multiplier in Q, done. Multiplicand is in B, multiplier is in Q. Then I will find the sign bit of the result. I just told you that we do an exclusive OR of the multiplicand and multiplier sign bit, and when we do a XOR we will get the sign bit of the result. So the result will be here. So I will put this will be the sign bit of the result. So I have done this. This is done. I have just found the sign bit of the result. Then I will initialize. I will put 0 in A. So in A register, all zeros, and in E, there is a continuous 0 going in. And in this sequence counter, I will store 5 because the multiplier has 5 digits. So here it is written n minus 1 because minus 1 is of the sign bit. Multiply will have 6 digits, one for sign bit, but we are here see in sequence counter we only need to store how many bits are there in the magnitude of the multiplier. That is why this is n minus 1, not considering the sign bit. So let us start. First thing I have to do, I have to see qn. Qn, I just told you that it is the, we have kept this as the name of the rightmost bit here. So what is this rightmost bit? Q register's rightmost bit can be seen here. It is 1. So I write here Qn is 1. Qn is 1. That means I have to follow this path. I have to do A plus B and store the result in A, and if there is an extra bit, store that in E. So do an A plus B. So add B. So this is B, 1 0 triple 1 here. So with A you have to add this 1 0 triple 1. So we will add this A and B and store the answer in A. So after adding these two we get this thing and it remains as such. Then the next thing the flowchart tells us is that do a shift operation. So I will do a shift operation. What I have to shift? EAQ. I have to treat it from here up to here as a single unit, from this thing to this thing as a single unit, and I have to do a right shift from here to here. So when I do a right shift, what will happen? This qn bit will go out and other bits will move this way. The last bit of this register will go here and it will move right, and this E will come here and E will be replaced by 0 from here. So I have done a right shift here. Let us do a right shift as the flowchart is telling us do a right shift. So I am doing a right shift here. EAQ. So here I am doing a right shift. You can see. So this 0 comes here. This 1 0 triple 1 goes here. 1 0 1 1 and 1. And 1 0 0 1 1 is here. 1 0 0 1, and the last one is discarded. It goes out from here because we have done the right shift. And then the flow chart says now decrement the counter. So I have decremented the counter. The counter was 5 initially, now it is 4 here. So from where did this logic come? This logic has come from here, because in normal multiplication we also do a similar thing. When we perform this, for example, this is to be multiplied by 1 and we get this, then we get a second thing, then we do an addition, and there must be a right shift here. The right shift is used to eliminate this bit. Once we multiply this with 1, 1 is done, so the right shift is used to delete this one. Then after another multiplication of this number with this one, again a right shift will be done so that this will be removed. So this way we move forward. So this is a very logical procedure. So let us move forward now. Now we have done one iteration. Then we will check SC, the sequence counter. Sequence counter contains 4. So that means we will go this way. Again check Qn. What is Qn? The last bit of Q, it is 1. So when it is 1, we have to again do addition A plus B. then a shift operation, then decrease the sequence counter. So do a plus, this thing is to be added to B, we will get this thing, and then do a shift. So whole this is shifted, so this one comes here, this is shifted, this is also shifted, so this one goes out. So after shift we get this thing, then we decrease the sequence counter, it comes out to be 3. Then this is 3, so again we go this way, again check Qn. Now the last digit of Q is 0. Since it is 0, we go this way. Now when we go this way, we have to do only shift right. So just do a shift right. If since Qn is 0, do a right shift. After right shift we get this, decrease the sequence counter. Again this is 0, so again this is 0, means go this way, do a right shift and decrease the sequence counter, do a right shift. So here a right shift has been done to this thing and decrease the sequence counter from 2 to 1. Now the sequence counter is 1. Sequence counter is 1 means we go again this way. Again check Qn. So what is Qn? Qn right now is 1. So since Qn is 1, we go this way. We do addition followed by shift followed by decrement in sequence counter. So we do addition. We add this A, contents of A are added to B, we get this thing. Then we do a right shift of whole from here to here. After right shift we get this thing, and the sequence counter is decreased, which becomes 0. Since the sequence counter has become 0, that means we go this way and we reach to the end of the flow chart. So the end of flow chart reads that you have found the product. The product is in AQ, means you have to see from here up to here. So these two registers combined will be the product. And obviously we know the product will be large, very large number. It cannot be stored in a single register. That is why this mechanism is there. So the answer will be in whole these two registers, starting from here until up to here. So if we see from here, starting from A up to the end of Q, this whole is our answer. So this whole is our answer. So and if we check this thing, this will come out to be exactly 437, this thing. So this will be 437. Will it be positive or negative? That has already been decided by this operation. If this is 0 here, this is positive. If this is 1, it is negative. In this case, obviously it will be a positive thing. So the answer will be positive. So this whole thing is about multiplying two signed magnitude numbers. Multiplication of signed 2's complement numbers. Those numbers where the negative number is represented in terms of 2's complement and the positive are represented just by a sign bit and a magnitude. Those types of numbers we will take up and see how they can be multiplied. For multiplying signed 2's complement numbers, we use an algorithm, a famous algorithm that is called Booth multiplication algorithm. The algorithm is a simpler one. Let us see the flow chart for the corresponding algorithm. So here on the left side of your screen, you can see a flow chart. This is the Booth algorithm flow chart. So the flow chart says that when you have to multiply two numbers, two binary numbers, put the multiplicand, the first number in BR register, put the second number, the multiplier, in QR register. Then clear the accumulator AC, the accumulator register, clear it. In other words, put all zeros in it, and then take a flip flop which will hold 1 bit, put 0 in that flip flop, use a sequence counter register and put n in it, where n is the number of bits in the multiplier. So if it is 5, if we have to multiply something by 5 digits, 5-bit number, so it will be 5. So these registers are shown here in the hardware circuit. This thing shows us that to multiply using Booth algorithm, you need this hardware. You need S1 and 2 registers for holding the numbers. In BR register, you will put multiplicand, and in QR, you will put the multiplier. And an additional register AC. And after multiplication, the result will be stored in both these registers. Since the result obviously will be a larger number, it will not fit in a single register. It will be stored across this thing. In addition to this, we need a sequence counter, a register which will store the number of iterations we are done. And an extra flip-flop will be required, a 1-bit storage which will store certain bit. So coming back to the flow chart, after doing these operations, you have to go for a check. Diamond represents a condition. So you have to check a condition. What is the condition? Qn and Qn plus 1. Qn means the last bit of Qn of register QR. So you have to check these two last bits, the last bit of this register and this 1 bit. What are their values? Since they are 2, so there will be 4 combinations. Either these two together will be 0 1 or 1 0 or 0 0 or 1 1. So based on this thing, here we have 3 paths. So if the value is 0 1, go from here, just do an addition and store the answer in AC, then do an arithmetic right shift of both AC and QR. Then decrease the counter, again check the counter. If it is not 0, restart, again check. If it is 1 0, go this way, do a subtraction. So this is a subtraction operation. So do a subtraction and store the answer in AC and follow this again, this path. And if it is 0 0 or it is 1 1, then neither do addition nor subtraction, just go this way and do an arithmetic shift. And this process of iterating will continue to the point when SC will become 0. Once it becomes 0, so you have to end, and that time you will get the answer, and the answer will be stored in, it will be from here to here. So the answer will be in AC and QR. To understand this flow chart properly, let us take an example. So let us say we have to multiply two numbers, -9 and -13. So this -9 will become the multiplicand and -13 is the multiplier. So since the Booth multiplication algorithm works on 2's complement numbers, so we have to take 2's complement of, we have to represent -9 and -13 in 2's complement. So if we find the 2's complement of -9, 2's complement representation of -9, that will be equal to the 2's complement of +9, that is this thing. And if we take +13 and do a 2's complement on that, then that will become -13, that will be this number. So this number is -9, this number is -13 in 2's complement. So let us start with the flow chart. First, I have to put multiplicand in BR. So the multiplicand is -9, which is this. So I will put this into BR. So in BR, I have stored 10111. And the flow chart says multiplier in QR. So here I have QR in this table. So in QR, I store -13, which is 10011. This -13 I store here. Then the flowchart says that clear AC to 0, put 0 in Qn plus 1 and put n in SC. So let me initialize, put zeros, all zeros into AC, put 0 into Qn plus 1 and initialize this SC, which is same as n. N is the number of bits in QR, which is 5. So I write 5 here. 101 means 5. Then moving further in the flowchart, check Qn and Qn plus 1. So Qn is the last bit of QR. So Qn is 1 and Qn plus 1 is 0. So the combination is 1, 0. So in the flowchart, I have to go this way then, 1, 0. If I go this way, it says subtract, do AC minus BR, AC minus PR, which is same as AC plus BR bar plus 1. So we do a subtraction. 1, 0 is there, so we do a subtraction. So subtraction means this AC is to be added to BR bar. So BR bar plus 1, in fact. So when we add these two, which is same as the subtraction operation of AC and BR, we get this thing. So we get this thing. Now the flowchart says that the next step you have to do is an arithmetic right shift. Arithmetic right shift of AC and QR. So this thing, AC and QR, I have to do arithmetic right shift. So all bits will be shifted by 1 to the right. That means the last bit of QR will go here into Qn plus 1, and others, the last bit of AC will go to this place, and there will be a shift. Now an important point to remember here is that we are doing arithmetic right shift, ASHR. So when we do an arithmetic right shift, we need to preserve the sign bit. So we need to preserve the sign bit. Since this first bit here is the sign bit, so we need to preserve the sign bit. So after doing the shift, I have to check what was the sign bit earlier in AC. If it was 0, the empty space will be filled with 0. If the sign bit earlier was 1, this empty space will be filled with 1. This is what we call as arithmetic right shift. So let me do this arithmetic right shift on this AC and QR. So this 0 1 0 0 1 will come here, 0 1 0 0 1. Then this 1 double 0 double 1 will go here, 1 double 0 double 1. So this one goes here, and this Qn plus 1 contents are overwritten. And then the flowchart says after the shift, just decrement the counter. So I have decremented the counter from 5 to this is 4. Now after that, check the counter. Is it 0 or not 0? It is not 0. So go this way. Again check Qn and Qn plus 1. So what is the Qn and Qn plus 1 after here? It is 1 1. If I see, this is Qn, this is Qn plus 1, this is 1 1. So 1 1 means this route I have to take. The flowchart is saying take this route. So I don't have to do any addition or subtraction. Do an arithmetic right shift and a decrement in the counter. So 1 1 means arithmetic right shift. So I will shift all these bits to the right. So 1 will go here, all will be shifted to the right. But when we do an arithmetic shift here and here every time, I have to keep the sign bit as it is. The empty space will always be filled with the sign bit. Since here AC was 0, starts with 0 positive, so here also in the empty space I have put 0. Again after right shift here, there is an empty space here that will be filled by 0 because earlier it was 0. Okay, now this is done. The counter is 3. This is 3, so we will go this way. Again check Qn and Qn plus 1. So what is Qn and Qn plus 1? 0 1. So 0 1 means this way. So I have to do an addition, then a shift, and then a decrement in the counter. So 0 1 means add BR. So you have to add to the contents of AC, you have to add BR, then store in AC. This is the answer. Then the flowchart says do an arithmetic right shift. So I will shift AC and this QR to the right. So here we can see that after shifting, there will be this one has come here. This first one has come here. Second one is here. 0 0 is here. And this one is here. And so on. And the first space that became empty is to be filled with the sign bit of the earlier number. So earlier it was 1. So here the empty space will again be filled with 1. So after doing all this thing, you decrease the counter, it becomes 2. Then the flowchart says, again check this. So it is now Qn is 0, Qn plus 1 is 0. So 0, 0. So 0, 0. On 0, 0, the flowchart says, just do an arithmetic right shift. I am doing an arithmetic right shift for whole this AC and QR. So once they will be shifted right, there will be an empty space. That empty space will be filled by 1 because earlier it was 1. Counter will become 1. Again, I will check these two. So this is 1, this is 0. 1, 0. So the flowchart says when it is 1, 0, do a subtraction. So I will do a subtraction, which is same as adding the 2's complement of BR. So I will do that operation, I will get this thing. Now I have to do shift. So this is AC, this is QR, do a right shift. So after doing the right shift, I get this thing. The empty space is filled with 0 because earlier it was 0. And decrement the counter, it becomes 0. Since the counter is now 0, the flow chart says that now you have to go in this direction. So going by this direction, I reach to the end, which means I have found the result. Where is the result? The result is in AC and QR. So you have to join AC and QR, then only you will get the result. So the result will be from here to here. So let me see what is it. So from here until here, total 10 bits result. So since it starts with 0, that means it is a positive number, and the remaining will be its magnitude. If I convert this thing, I get 117 in decimal. So I can cross check. If I multiply -9 and -13, I get plus 117. So the answer is correct. Likewise, you can take some other example and execute that example on this flowchart, and then you may also cross check the result. Thank you.